Hi, everyone. I'm going to start off today talking a little bit about Kenken. It's a type of Latin square puzzle like Sudoku where the goal is to fill in the cells with symbols from some set so that each symbol appears exactly once in each row and once in each column. In Kenken, we have some additional constraints given by those heavily outlined regions, which we call cages. And when you apply, each one of these cages has a clue in the form of an operation and a target. When you apply the operation to all the cells in the cage, you need to arrive at the target. So on the upper right-hand corner, we see that if we add these three together, we need to get to 11. Or here we see if we multiply these 5 together, we need to get to 36. But this is not the puzzle I want to talk about today. I mean, it's sort of arbitrary as to see which operation ends up in which cage. And the clues, they're not even in the same set that we're using to fill in the cells. So this is a puzzle I like much better. This is a puzzle over the cyclic group of order 4. We're just in the integers mod 4 under addition. And you'll see that the operation's understood to be the group product. And suddenly all the clues are in the same set that we're filling in the cells with. And at G4G13, what I talked about was exactly this, cyclic group puzzles over the group of order 4 with this cage pattern. Now, there's a good reason to study puzzles with this cage pattern because this is actually the only cage pattern under reasonable conditions that has a chance for unique solutions. But I feel kind of bad about that talk because I left out the other group of order 4, so I wanted to come and talk a little bit about puzzles over the Klein Four group today. Now, there's many ways to look at the Klein Four group, but probably for purposes of this talk, we just want to realize that anything squared is the identity, and the product of any two non-identity elements is the other non-identity element, sort of like the Grimes dice, or what Hamilton etched into the bridge, but the direction doesn't matter. So the first question you could ask is, does every puzzle have a solution? So in order to answer that, look at the following puzzle over here, where we have these two clues on the top that are the same. So we have a full puzzle, but we don't care about the bottom half. Let's just look at this top half. Well, if we fill in the rows, we know that each row has to contain each element of the group exactly once. So this row has to have EA, B, and C, and this row also has to have EA, and B, and C. And since anything squared is the identity, if we multiply the entire top half of the board, we need to get the identity. But the clues are the same, so if we multiply those cages, these cages here, we're going to get W squared, which is also the identity no matter what W is, which means the product of these two must be the identity, which means they must be the same over the Klein Four group, which means if you have a puzzle with adjacent equal clues, it would violate the Latin squared condition if you wanted to solve it. Now, this is the exact opposite of what happens in the case of the cyclic group of order 4, where you actually need puzzles with adjacent equal clues in order to get a unique solution. So, I mean, we could ask, does a puzzle have no solution? Yes. Do some puzzles have more than one solution? And the answer to this is much simpler. Well, any Latin square could be used to make a puzzle. You just make the clues fit whatever that Latin square is. There's 576 Latin squares. There's just not enough puzzles to go around. So of course, we're going to have some puzzles with multiple solutions. So then the real question that we probably want to know is, given a puzzle, how many solutions does it have? And in the time we have here, I'll just discuss the strategy for doing this. So probably the best way to do this is to find some group of transformations that ends up fixing not the solutions, but ends up fixing the number of solutions that puzzles have. And then you can just take one element from each equivalence class, and you can just study some very small set of puzzles and get information about everything that could possibly happen. So what kind of maps are going to fix the number of solutions? Well, you can look for group automorphisms. Obviously, if you apply an automorphism to the clues and you apply it to the solution as well, the new puzzle you're going to get is going to have the new solution because, well, the product is preserved. You could also rotate and reflect given this cage pattern, because if you take a puzzle and you're holding it like this and you solve it, and then you turn it like this and you solve the same puzzle, well, it's going to change where the elements appear, but it's not going to change the number of solutions. But over the Klein Four group, you actually get an additional type of map where you can just multiply anything by any element of the group you want. So if you multiply both the clues and the solution, You're going to change each of those cages by g cubed, but since g squared is the identity, you're going to end up changing everything exactly by g, and you're going to get a new solution that fits your puzzle. So we have a very large group of transformations here. We have a D4 crossed with S4 action when we put it all together, and that gives us the following table of only 7 puzzles we need to study. And we've already studied 4 of them, because 4 of them end up having adjacent equal clues. So there's actually only 3 cases that allow for the possibility of solutions at all. And you end up getting 4, 8, or 12 solutions. Now, 30
seconds.
Oh, yes. So the only thing I have left to address is, first of all, you can still get unique solutions by filling in individual cells, so you can make interesting puzzles. And there was no 13 at all in my talk. And I really wanted a 13 to come out somewhere. So the number of ways you can solve this puzzle or decide not to solve it is exactly 13. Thank you very much. If you like these kinds of puzzles, feel free to visit my free puzzle blog. I have puzzles over all different mathematical structures.